Okay, so what this should do, as we change the value of 20 there, right? This should produce different graphs. So let's say we say here, let's say table H goes to, let's say 5 to 25. Steps of 2, just for good measure. Why is this taking so long? Oh. Okay, what the hell are those? So basically, this thing is going to become a complete graph. If the thing is somehow ergodic, it's going to become a complete graph.
Yes, that sounds right.
But honestly, it's a pretty complete graph in all these cases. So maybe we should try a different underlying function. What underlying function should we try? We could try just the fractional part of 3, fractional part of 2 case. I don't know what these mean. Okay, what this is showing is the epsilon balls around, at every step, we're generating this thing, and then we're looking at the symbolic dynamics of the thing. And I mean, I think this is very traditional dynamical systems theory again. I think all this is doing is, this is looking at the transitions. I think all you're seeing here, yeah, all you're seeing, every edge is just a transition of the individual symbolic dynamics. And this thing, yeah, this is just filling out the symbolic dynamics of the system. So that's actually kind of interesting that basically what this is telling us is multi-way systems don't make any sense for real numbers in a first approximation. Jonathan and others.
Well, they do, but you need uncountable codomains.
Well, but they're not very interesting because what we're seeing is, what we see here is essentially just a picture. In both cases here, we have seen the same thing as ordinary sort of unary symbolic dynamics.
Yeah, because we have countable codomains.
No, we don't. We can have an infinite ensemble in the other case as the initial condition.
Yeah, but we still have countable codomains.
What does that mean?
The codomain of our function is a countable set.
Explain. Don't understand.
There are 2 values in your list. Or 3 values, I forget.
And what
the
do you
state evolution
think?
function
We have to have an infinite number of values in that list.
It maps a single state onto 3. But in order for it to be a measure-preserving transform that's non-trivial, it has to map a single state onto an uncountable set of states.
Well, or alternatively, it could be mapping. So you're saying, okay, so the next case is mapping every value to a kernel, basically.
Right. Yeah, I mean, that was the point I was making, that you have to have a state evolution function that produces an uncountable set of states. And then I conjectured, although I haven't yet been able to prove, that that should be the same as having everything going a countable number of states, but where effectively your time interval goes to 0.
Okay, but look, this thing here would be something like x goes to,
Right.
Normal distribution or something.
Exactly. Yeah, it goes to an interval. I mean, the point I was trying to make, earlier when I first raised this, was that if your states can take values from an uncountable set, but you're only mapping to countable sets, you obviously can't preserve measure in any non-trivial way.
Okay. But so in this case here, we're saying, but by the time you're doing this, it doesn't make any difference that you have a list of things in the multiway system. You're just mapping every value to some distribution, right? Couldn't care less that this maps to, we could say x goes to normal distribution and Poisson distribution, but who cares? Right? You could just combine those distributions.
No. The distribution is the list.
I know that. I realize that. That's why I'm saying.
What do you mean it doesn't matter?
It doesn't. It's just a very traditional system at this point. It's just mapping. Well, you're saying it's not so traditional, I guess. If you map,
I'm not aware of anyone who's investigated this.
It's like an integral equation. It's like a discrete version of an integral equation. Right. So every value. So after just one step, you no longer have a discrete set of delta functions. You've got a continuous distribution, right?
Right.
Okay, so at every step, you're mapping that distribution to another distribution, and all you're doing is taking the integral, right, of this kernel with what you've got, right? So at every step, at each step, you are computing integral of the kernel function, whatever your kernel function is, dx or something, times your function f of x plus dx.
Right, but but it's not an integral because the overlaps are subtracted.
What?
I mean, that's what a multiway system is, right? That's the notion of merging.
Ooh, let's think about that for a second.
Wherever you get an overlap between two distributions, those states merge. So what you're describing, it would be a pure, in the same way as an ordinary multiway system is a tree if you set and include if you include state IDs for everything. The continuum case would be an integral if you include state IDs for everything.
Okay. Assuming no merging.
Right.
And
but just like, in ordinary multiway systems, that's the boring case. It's also the boring.
I understand. Assuming no merging where the pure discrete multiway system would be a tree.
Right. But what we're actually getting is some, it's an integral with an uncountable set of bits cut out of it.
Well, let's think about that for a second. So we're coloring the kernels. We're saying we've got certain kernels. We've got different colors. This isn't in fact correct what I wrote here. Instead what we've got is we've got this, and we've got the normal distribution is red and the log normal distribution is green. Something like that. Right, so first element is red, second is green. Okay, and what we're saying is that wherever red and green overlap, what are we doing with them?
Then we only count one or the other. Right.
Right.
That's picking which branch to resolve to.
Right. Okay, so we're saying, so at every step, we compute this integral for each one of these, and then we look at, so let's do this for a particular case, okay? So how do we do this? This is a convolution integral. God, I haven't used convolve in a million years. So it's a convolution of like a Gaussian, let's say. How does convolve even work? Okay, how does this work? So we're saying of, oh gosh, we have to have an empirical function here, don't we? Well, we could just take the sum of the values, right? And in other words, we're just taking, no, we can't take the sum of the values. The sum of the values, do you understand my problem? I mean, for every value is a delta function.
Right.
Right, at any given stage, every value is a delta function. This is a quintessential Monte Carlo integral problem, I think.
Right. Right. It's just that the region you're sampling from is non-trivial.
Right, but so what's going to happen is that this thing is going to end up with slicing itself up finer and finer with what's red, what's green, etc. But at every step, what the heck are you doing? At every step, what you're doing is you're taking the sum of these values, the sum of the distribution. So the distribution has some probability, P of X, which you could normalize. That's, normalizing the path weights, you could normalize that. So this is saying for every value of X, you are always taking minus the overlap. It's some kind of probability distribution. So it's, what the heck is it? It's so given two P of X values, right? For a given X, we have P1 of X from one kernel and P2 of X from the other kernel, right? So what is this saying? This is saying what is this saying? How do you combine these two values? Well, you're saying it's the max of P1 and P2, right? It's simply equal to the max, combining it with max, if I'm not mistaken.
I mean, that's one, it's as in the discrete multi-way case, that's one possible way of choosing which, how to merge.
How else would you do it? Because that's keeping the measure of what.
Right, but you could have a causal invariance violating system which merged with criteria merged with effect of min.
Okay, fair enough. All right, so this thing. So what's interesting about this is, so this gives you essentially a Monte Carlo. It's very similar to the things people have been doing for these models of what am I saying? These contagion models and things, I think.
Interesting.
You basically have to Monte Carlo it all the way through. But I would guess, so in this case, all right. So one thing we're learning from this, I mean, it gets quite squiggly when so if we do this, then at every time step, So my question now is, what about continuous time?
Yeah, so as I was saying, my conjecture is that if you take the limit as your time interval becomes infinitesimal, that will be no different to this limit of the codomain becoming uncountable.
That's not obvious to me because combining with max, what does this mean? So it's
right?
a PDE.
Because if each of it, okay, if you start off with a unit time interval, right?
Mm-hmm.
If your time step is 1, and at each time step you're increasing the number of states by some countable amount. Then you take the limit as the time interval goes to 0. Now in a unit time interval, you're going to increase the number of states by an uncountable amount.
Yeah.
So my presumption is that the continuous time limit will dominate over the continuous, will imply the continuous branch limit.
Oh, I'm sure that's true. But I mean, the question is, what kind of a system, what kind of a mathematical system is it in continuous time? So in this discrete time case, it's a pretty weird convolve and max story.
Mm-hmm. Right, but you see my point, that they're actually the same case.
Explain again.
Well, so if you consider the continuous time case, but you sample at discrete intervals, it will look the same as the previous case.
Why?
For the reason I said, right, that you're taking the unit time interval, you're crushing it down so that in each infinitesimal, with each infinitesimal time step, so to speak, you're increasing the number of states by a countable cardinality. So then in the unit interval, which is the discrete thing you're considering before, you're increasing the number of states by an uncountable amount.
I understand nominally that cardinality argument, but I don't understand what that means. If I were to take the single, let's take the limit of a single.
If you take an uncountable union of non-empty disjoint countable sets, you get an uncountable set. That's all I'm claiming.
Okay, let's take the very trivial example, no branching. Okay, if we have no branching, this is an ODE, isn't it?
Sure.
Is it an ODE or is it a PDE? Hold on.
The state corresponds to a single parameter family.
Wait a minute, but we've got an interval here. No, I think it's a PDE, right? Because we got the interval, we've got the initial interval, and then at every step, we need to make a change. So in the previous case, in the previous case, okay, in discrete time with no branching for discrete time, this is a discrete time case. It's a convolution, right? It's a convolution in that case. Discrete time, it's an iterated convolution. Correct?
Sure.
Okay, so what is the continuum limit of an iterated convolution?
But wait, so in the continuous time case, you're asking about the situation where the initial condition is not a state; it's an interval.
Yes, because after
okay, then fine. Then it's a PDE.
Otherwise, just a PDE with a delta function initial condition. Right. Notice though that a PDE is a very specific class of things that have been made nice for the case of continuous time. I mean, PDE is just a very civilized thing that you can do.
Yeah, it's a sequential substitution system. There's no multi-way branching.
No, in this case, I agree. But more than that, a PDE is not the only. Okay, all right. So It's a PDE for continuous time. All right, so what is it when it has more than one thing? What's the analog of this combining with max at every step? What is the infinitesimal combining at max with max thing? It's really not obvious to me. I mean, unless it's some kind of weird path integral thing.
Right. But I mean, the point I was making is you can still do the combination with max at discrete time steps, even in the continuous time case.
Oh, you can choose to do that, but I don't think it's equivalent. I have no reason to think it's equivalent. What the heck is it, though? If you're doing an operation like that at every infinitesimal step, you're taking these two functions.
But I'm still confused. Are we considering a combination of the continuum branch case and the continuum time case, or are we considering the pure continuum time case?
No, we're considering the combination. We're considering the two together.
Oh, okay, fine. Sorry, I was talking about the continuous time case. Right.
The continuous time case with discrete branches is not problematic, I think. I agree with you in that case.
Okay, yeah, sorry. That's why I was confused. Okay, yeah, sorry. That was my mistake.
Right. The case I'm thinking about is the continuous time and continuous branch case. And I'm having a hard time understanding how you combine functions. Well,
it's kind
so
of a
hard,
light.
actually.
It's a light cone intersection kind of thing, isn't it?
Well, but why isn't it the case that just in your PDE, you just put a max in your PDE? I mean, it's not completely obvious to me that the whole thing is a PDE at all. I mean, it's a bunch of convolutions. It's more like integral equations. It's integral equations with some bizarre overlap condition.
Right. But you see my point, right? Instead of taking a p1 of x from one kernel, p2 of x from another kernel, at some instant of time, you're taking a finite interval of time, and then you're computing some intersection of light cones between those two.
Yes.
And then taking a max at the intersection point.
Yeah, no, I
At
agree.
the tip of the light cone.
It's complicated. Okay. One last question, and then we should wrap here. Maybe we should really wrap. But in the discrete case, if we were to take the limit of an infinite number of steps, okay? I mean, so this is the, this is a different case. This is a discrete iteration, infinite number of steps. Do we get a transfinite number of, I mean, we get transfinite trees at that point. So I'm saying, I mean, discrete iteration.
Right. The trees themselves are transfinite, but the branches are still countable. I think.
At every step, the branches are countable.
Yes.
Yeah, but my question is, what is the limit? Like, let's take our friendly tree, you know, one of these this was the, you know, this creature, right? What is the infinite time limit of this creature? I mean, the infinite time, what can we say about this? By the way, in the what is the way to think about this in the real number case? Well, okay, it requires more thought. We should probably wrap this up here. All right. Well, this was good. Thanks. Oh, it looks like our streaming thing died, but we were recording this, so we can knit this back together again, and yeah. All right.
Very interesting stuff.
Yeah, and let me just look at the things that were on this. Oh gosh, Charles sent something like millions of years ago here.
Yeah, a nice labeling. And mine at the end is a curious property of the plastic constant.
Well, Ed, I don't know what to make of that. Okay. What am I supposed to make of this?
It's the best distribution for all values.
Okay.
If, for example, if you use pi instead, the points would be closer together.
Yeah, I understand. It clumps. This is the most unclumped. It's an unwinding of some kind. It's a two-dimensional analog of the Fibonacci of the golden ratio thing.
Yes.
It's cool. Cool, actually. All right, another interesting session, and yeah.